Hello students, and welcome back to my class. So in the last lecture I had started with ring theory, the concept of rings, and I had given you some examples. Okay, so let us begin from there itself. So one problem that I gave you was to show that the set of complex numbers with the usual addition and multiplication of complex numbers is a ring with unity. Okay, is a commutative ring with unity. It's commutative as well. Okay, so this is what I had given. So let us see how to show this. So showing such sets as a ring is nothing but a routine exercise to list the properties of the rings. Okay, that we have already done. So step by step. Okay, so let us see. Let C equal to set of A plus IB such that AB belongs to R, and let Z1 equal to A plus IB and Z2 equal to C plus ID be any two elements. Okay, then addition and multiplication in C are defined as this. Okay, so this is already known to you in higher secondary classes. We have done the sum of two complex numbers is just the real parts are added together and the imaginary parts are added together. Okay, and Z1 Z2 is defined as AC minus BD plus I into BC plus AD. Okay, right, so that way the addition and multiplication is defined. So by definition of addition is closed because this is also a complex number. Okay, A plus C is real, B plus D is real, so it's real plus I into real, so it's a complex number. By definition, Z1 Z2 is also a complex number. Okay, so we don't have to worry much. Okay, so number one, we can just write from definition of addition, Z1 plus Z2 belongs to C for every Z1 Z2 belongs to C. Okay, so C is closed under addition, no problem. Okay, we can also write that it is known that the addition of complex numbers is associative, or just we can show it. It's very simple. Just Z1 plus Z2 plus Z3 inside bracket. Okay, so we can add these two together and then apply the definition of addition of complex numbers, and then we can use the property that addition is associative in R. So A plus C plus E can be written as A plus C plus E. Okay, like that. Okay, so this will be same as Z1 plus Z2 plus Z3. So addition is associative in C. Okay. Next, you have the zero complex number, which is 0 plus I0. So it's a complex number, and it satisfies that any other complex number plus 0 is the number itself. Okay, so this is what I have shown. So 0 is the additive identity. Okay, then for any Z1 inside C, we have minus Z1 equal to minus A minus IB. Okay, so this is also a complex number, and the sum of these two complex numbers is 0. So that means minus Z1 is the additive inverse of Z1 inside C. Okay, and the fifth one, we have the commutativity of addition. Okay, so this also you can just demonstrate. A plus IB plus C plus ID is A plus C plus I into B plus D. A plus C can be written as C plus A because addition is commutative in R. Okay, here it will be R. Addition is commutative in R. Okay, so it's R. So please note it down. It's R. Okay, so Z1 plus Z2, Z2 plus Z1. So addition is commutative in C as well. Okay, so by definition of multiplication, Z1 into Z2 is inside C for every Z1 Z2 inside C. So C is closed under multiplication also. Okay, and number 7, we know by rules of or properties of complex numbers, multiplication of complex numbers is associative. Okay, then left distributive property holds Z1 into Z1 Z2 plus Z3. These are just properties of complex numbers, so we don't need to prove so many things here. So we just know these properties. Okay, and then what is the identity element? What is the unity element? It's Z equal to 1 plus I0, that is the number 1. Okay, 1, any complex number multiplied with 1 is the number itself. Okay, so this is what we have shown. Z1 into Z is Z1 for every Z1 inside C. Okay, that means Z equal to 1 plus I0, that is 1 is the unity in C. So it's a ring with unity. Okay, numbers 11, we have to show that it's commutative. So we don't know by multiplication properties of complex number, multiplication is commutative in C. Hence, C is a commutative ring with unity. Okay, so this is what we have shown. Let us try another problem. So in the earlier class, we have done that the set of 2 by 2 matrices over R is a ring. Okay, So here let us start with any n by n matrices. So that the set Mn of all n by n matrices over R is a ring with unity with respect to usual addition and multiplication of matrices. Okay. So let us just define what are those addition and multiplication. So let ABC belongs to Mn, Bn, Dn elements, and let A equal to Aij n by n, B equal to Bij n by n. Okay, that means ijth element of A is Aij. Okay, like that. Then addition and multiplication of Mn are defined as A plus B equal to the matrix where the ijth element Dij is the ijth element of A plus ijth element of B. Okay, this is how addition is defined. And multiplication is defined this way: the ijth element of the product is equal to summation over ikth element of A multiplied with kjth element of B. Okay, so this is the definition of matrix multiplication. So by definition, the sum and product of two matrices is a two n by n matrices is a n by n matrix. Okay, so there is no problem with the closure property. Okay, so we can write by definition A plus B belongs to Mn for every AB inside Mn. So that is Mn is closed with respect to addition. We know matrix addition is associative. Okay, so these are just simple properties. And let 0 be the null matrix of order n by n. Null matrix means every element of that matrix is 0. Then A plus 0 is A equal to 0 plus A. These are the properties of null matrices, or just by addition we can see. Okay, so 0 is the additive identity. Then for A equal to Aij inside Mn, we have minus A is the set of all those elements. Minus A is the matrix whose elements are minus of the negative of the elements of corresponding elements of A. Okay, so A plus minus A is 0, which is same as minus A plus A. That means minus A is the additive inverse of A in M. Okay, then we show the commutative property of addition. Okay, so it's just simple: Aij plus Bij, it can be written as Bij plus Aij because these are real numbers. Okay, and we know real numbers addition is commutative. Okay, so addition is commutative in Mn also. Okay, then by definition the closure property is satisfied: the product of two n by n matrices is an n by n matrix. Okay, then we know matrix multiplication is associative. Okay, so this for these also proofs are there, but it's not necessary to do those proofs here. Okay, so by properties of matrices, so these are also properties of matrices: distributive, left distributive property, right distributive property. Okay, all these are hold. Okay, one thing is left, that is, so till point number 9 we have shown that the set Mn is a ring. Okay, the next I have to show that it's a ring with unity. So what is the unity element? It's the identity matrix here. Okay, let In equal to Eij n by n, where so what is the definition of identity matrix? The ijth element of the identity matrix is 1 if I equal to j and 0 if I not equal to j. That means only the diagonal elements are 1, everything else is 0. Okay, so then let this be the identity matrix in Mn. Then A into identity matrix is A, which is equal to identity matrix into A. Okay, so therefore In is the unity in Mn. Okay, hence Mn is a ring with unity. Right, so the set of matrices n by n matrices with respect to usual matrix addition and multiplication is a ring with unity. Okay, but it is not a commutative ring. Okay, just as before in the earlier class also we have seen this small example: 1 1 0 0 multiplied with 1 0 1 0. Okay, so it's not commutative. Okay, so the same example will work here as well. We take all other elements as 0, only the 2 by 2 submatrix we take as 1 1 0 0 and 1 0 0 1 0. Okay, so if you take the product, you will see. So the finding out the product of these two matrices is very simple. We just find out the product of the 2 by 2 submatrices. Okay, so you see these two matrices are not equal. Okay, they are different, right? So AB is not equal to BA, so it's not a commutative ring, right? Okay, now let us see some properties of rings. Let A, B, C belongs to R, where R plus dot is a ring. Then A into 0 equal to 0 into A equal to 0. Okay, so what are these properties? These properties are basically, if you compare with the properties that you had learnt in school, these are just we had taken these for granted. Okay, so what is the reason for listing these as properties is that from the definition, okay, the definition uses only the minimum number of properties that are taken as granted. Okay, all other things are derived with those properties. Okay, so we do, in the definition of a ring, we do not give this property. Okay, because this property can be proved by the things that we have assumed in the definition. Okay, so the definition always gives us the least number of things that are required to build up a concept. Okay, so to build up these things, a into 0, any number multiplied with 0 is 0. Okay, to build up these concepts, only those definitions are necessary. Okay, so nothing else. So we will take these things as a theorem. So in any ring, a into 0 is always 0 into a equal to 0. A into minus b, okay, a into the additive inverse of b is same as minus additive inverse of a into b, which is also same as additive inverse of ab, okay, of the product ab. That means minus can be placed anywhere, right? And that is the meaning. Then minus a into minus b is ab. Okay, so this also we have been doing since our childhood. Minus into minus is plus. Okay, so all these things can be proved if we assume the laws that we had listed. Okay, the properties of rings. Okay, so minus a into minus b is same as ab. Then a into b minus c is ab minus ac. Okay, so this distributive law holds for subtraction also. Okay, so here in ring we don't have subtraction, we have the inverse, additive inverse operation. Okay, so it's analogous to subtraction. So further, if if R has unity element, then minus 1 into a is same as minus of a. Okay, and minus 1 into minus 1 is 1. Okay, all these things can be proved from the properties that we have listed. Okay, so let us see the first one. We have 0 plus 0 equal to 0. This is the property of the identity element, additive identity. Okay, any element plus the identity element is the element itself. So in particular, 0 plus 0 is always 0. So if you take a as any element, you multiply both sides. This is a into 0 plus 0. This element is same as this element a into 0. Okay, right? And then you apply distributive property. So a into 0 plus a into 0 can be written as a into 0 plus 0. Okay, this is again the property of identity element. Any element added with identity element is the element itself. So a into 0 can be written as a into 0 plus 0. Okay, but in the last class also I have noted, if R is a ring, then R plus is a group. Okay, and in the group theory you have already done that in any group the left cancellation law holds. Okay, what is that left cancellation law? It's a star b equal to, if a star b equal to a star c, then from this line we can write this will imply b equal to c. Okay, a can be cancelled. Okay, so this is the left cancellation law. In any group the right cancellation law also hold. So if you have say b star a equal to b star c, b star a equal to c star a, then this will imply that b equal to c. Okay, so these are the properties of groups. This is the left cancellation law. So here we have used left cancellation law to show that a into 0 is nothing but 0. Okay, then we have this ab plus its additive inverse, okay, is 0. This is always true. Now what is ab plus a into minus b? So that by distributive property we can write a into b plus minus b. So that is a into 0, but by the first property we can write this is 0. Okay, and now we compare this 2 and 3. This is also 0, this is also 0. That means these two elements are equal. So ab plus minus ab equal to ab plus a into minus b. Then again by left cancellation law, minus of ab is same as a into minus b. Okay, similarly we can show minus a into b equal to minus of ab. Okay, next is we already have ab plus its additive inverse is 0, and minus a into 0 is also 0. So instead of 0 we can write minus b plus b. Okay, and then again apply the distributive property. So it's minus a into minus b plus minus a into b. Okay, so this is there. Then you compare 4 and 5. These two are the same element. ab plus minus ab is same as minus a minus b plus minus ab. Okay, then we can apply the right cancellation law. You have the same thing on the right side. Okay, apply the right cancellation law. So you will get ab is same as minus A minus B. Okay. Then number 4 is quite simple. A into B minus C. What is B minus C? B minus C is nothing but B plus minus C. Then apply the distributive property A dot B plus A dot minus C. But we have already shown that A into minus C is same as minus AC. So it's AB minus AC. Okay, so this is also similar. Number 5 is also similar. Number 6 is we have A into 1 equal to A equal to 1 into A for every A inside R. So since 1 is an element in R, so minus 1 is also an element in R, and minus 1 plus 1 is always 0. Okay, so you multiply this by A, so it's minus 1 into A plus 1 into A is 0. Okay, but instead of this 0, again I can write minus A plus A. Okay, and 1 into A can be written as A. So again by right cancellation law, minus A into minus 1 into A is same as minus A. Okay, right. Then the next one, we have to show that minus 1 into minus 1 is 1. Okay, so we have minus 1 plus 1 is 0. So minus 1 plus 1 into minus 1 is what? 0 into minus 1. Same. These two elements are same. These two elements are same. So it's their product with minus 1 will also be the same. Okay. So minus 1 into, now apply distributive law, minus 1 into minus 1 plus 1 into minus 1. This is 0. Okay. So, but what is 1 into minus 1? We have already shown A into minus B is same as minus A into B. So, it's nothing but minus 1 into 1. So, it's minus 1. So, it is 0, which is 0 again can be written as 1 minus 1. So, again by right cancellation law, we have minus 1 into minus 1 is equal to 1. Okay. So, if a ring has a unity, then it is unique. Okay. If a ring has a unity, then it has to be unique. So there cannot be two unities inside a ring. Okay. So suppose that 1 and 1 bar be two unity in R. Okay. Then 1 into 1 bar is 1 bar. Okay. If we take 1 as the unity, so 1 into 1 bar has to be the number itself. That means 1 bar. Okay. Again, we take 1 bar as unity. That means 1 into 1 bar has to be 1. So 1 into 1 bar is 1 also, and 1 bar also. Okay, so from here itself we can conclude, yeah, okay, yeah, so from here itself we can conclude from 1 and 2. Okay, so 1 and 2 imply 1 is same as 1 bar. Okay. Right, because 1 into 1 bar, this element is the same as this element here, 1 into 1 bar. Okay, so it's quite simple. This portion is not required. Okay, so 1 and 2 imply that 1 is equal to 1 bar. Okay, so the unity element in a group is unique. Okay, so these are the properties of a ring, some properties. So there are some more properties as well, and we will also study subring. What is a subring? Okay, so in the next lecture we will study those things. Thank you.